All right, so we're going to start with a course review. We're going to start in Chapter 1 in Mechanical Systems and Equations. We'll start with mechanical elements, and then we'll look at Newton's second law, work and energy, and so on. We started off looking at just different types of mechanical elements. The first was a translational spring, which we drew using this like squiggly line. We'll say that the spring has a stiffness K. Displacement at the left is x1, displacement at the right is x2. Then the force for this system or this spring was equal to K times x1, or actually it's x2 minus x1. In general, x2 and x1 can be some complicated expression. Right now we're just representing what the deformation across that spring is. You can get a similar thing for a torsional spring, except in this case it's going to depend on rotations. Generally represented that using just a spiral, which is intended to imply that this thing deforms under rotation. We'll give this a stiffness of K sub t. The left will have theta 1, the right will have theta 2. And here the force is going to be equal to K sub t times theta 2 minus theta 1. We also looked at a nonlinear polynomial spring. Which we will indicate using just a regular spring symbol with an arrow pointing through it as shown here. Displacement on the left is still x1, displacement on the right is x2. And here we're going to give it two parameters, alpha and beta. Alpha will be the stiffness of that nonlinear spring. Beta will be the exponent, which we'll see in a moment. So here the force is going to be equal to that stiffness alpha times x raised to the beta. And here we're going to say that beta is some integer, some positive integer specifically. There is a way to extend this definition for beta to be any number, but we're not going to address that here. You can also extend this idea to torsional springs. In that case, it would depend on thetas rather than x here, or depend on x. Let me expand this. It will be alpha times the quantity x2 minus x1. This quantity raised to the beta. So it won't just be each individual displacement raised to the beta power, it's their difference or the relative displacement across the spring raised to that power. We then took a look at translational dampers. We drew using this symbol here. It represents a piston moving in a cylinder filled with some type of oil. This is where this viscous idea comes from. We'll give it a damping coefficient of B. You'll often see C used, sometimes D. It doesn't really matter. The key thing is that the parameter assigned to that damper is its damping coefficient. We'll say x1 dot on the left, x2 dot, because it depends on the relative velocity across that damper. So in this case, this force is going to be equal to B times x dot 2 minus x dot 1. You could extend that nonlinear polydynamic spring idea to a damper. It's just there isn't a physical representation for what that would be actually. If you were to, so we get this nonlinear spring from taking a regular linear spring and then stretching it transversely, so pulling it up rather than moving it to the right or left. If you do the same thing for a damper, you'll end up with a complicated nonlinearity that depends on both displacement and velocity. It's not just the damping like cubed or something. That's why I'm saying if you were to raise this to some beta power, that would not necessarily be a physical mechanical element. I mean, you can certainly do that in your system model, it just may not have any physical meaning. Mathematically, there's nothing stopping you from doing something like that. And we certainly didn't look at any nonlinear damping either. Last thing we looked at was a torsional damper. This is where we're really just going to extend this translational idea to rotation. We'll just kind of draw a damper that is curved, indicating that it deals with rotation. I have a theta 1 dot, theta 2 dot. It's really dealing with like angular velocities here, and we'll just say v sub t. For the coefficient, in this case then, our force will be equal to v sub t times theta 2 dot minus theta 1 dot. Right, so elements in parallel add together. If we put two springs in parallel together, we'll get that their combined force is equal to the summation of their coefficients, or K1 plus K2, multiplied by the displacement of that system, or X in this case. It's also true if we have a spring and a damper in parallel. And in this case, we'll get that their combined force F is equal to Cx dot. So that's the damping force plus Kx. That's our stiffness force. Or if we have two dampers in parallel, in that case, we would get that the force is equal to the summation of their components, C1 plus C2 times X dot. Then I also want to add a few more cases here. In this case, we're looking at two springs. They look like they might be in series, but we're looking at what's happening between the two springs, as shown here. This is equivalent to them being in parallel. And we'll talk about why, what's different in this case versus when we look at what they are in series. The key thing is that we're looking at the center of this point. The two springs are grounded on either side. Same thing if we were to put a spring on one side and a damper on the other. Oh, I'm sorry. Let me add a little expansion to this. This is true provided that there is a mass in between the two. Something like that. All right, we're going to correct ourselves here. The force in this case is going to be equal to m times x double dot plus k1 plus k2 x. So the point I wanted to make is that the elastic force is the same as what we had over here. Here we would get mx double dot plus cx dot plus kx. So ignoring that mass, that is equivalent. You have the same direction as well. All right. When we're dealing with springs in series, such as this case shown here, we're going to get that our force will be equal to some equivalent stiffness times the displacement x Our goal here is to find what K equivalent is, and we did that previously. K equivalent will be equal to 1 divided by K1 plus 1 over K2, and then the inverse of that. In the case that we have a damper and a spring in series, except for when there's a mass separating them, if there's no mass separating them, in this case we'll end up with, we won't be able to just simplify them like above. We'll end up with that the force is a first order differential equation given as shown. Where that force was equal to C times y dot plus K times the quantity x minus y. All right, we're going to move on to Newton's second law. We also call this vectorial mechanics because it focuses on using vectors, free body diagrams, etc. as a way to understand motion and find equations of motion specifically. We looked at two of them, two forms of that. The first is for translation. This is the sum of the forces, where the vector forces is equal to the mass times the acceleration. Where there's a vector, this is our acceleration. It's the acceleration vector specifically. We really only looked at 2D planar rigid body dynamics here, also particles in two-dimensional motion. In that case, for rotation, we had that the sum of the moments about the center of mass can be written as the position vector r crossed with the mass times the acceleration, or more commonly we would write it as the sum of the moments about the center of mass is equal to the mass moment of inertia about that center of mass times the angular acceleration of the center of mass. Or if you want to deal with some other point, you could do the sum of the moments about a different point, m sub o, and then this is equal to the moment of inertia about that other point times the angular acceleration about that point, where this IO is equal to the moment of inertia at the center of mass plus the mass times the distance from the center of mass to that other point squared. That's just our parallel axis theorem. we have a general problem-solving algorithm that we used. The first was that we would define a coordinate system. That includes choosing an origin, fixing a coordinate system for that, then also determining a direction of rotation. We would then go and define position vectors for every body. And once we found our position vectors, we would go and compute acceleration vectors. We'd start with velocity vectors. We'll just say determine velocity and acceleration vectors. And these three steps comprise what is known as kinematics. After that, we would go and draw a free body diagram for every body. I'm just going to write FBD for free body diagram for each body. And if needed, we would break up forces into components depending on what we needed out of them. Our fifth step then was to apply Newton's second law to each body. And you may need only the translational form or only the rotational form, or you may need both. It depends on the motion of the body. And then our sixth step was to then simplify as necessary and put our equation of motion into standard form. And these last three steps, those comprised of what is known as kinetics, which is specifically in this case relating the forces that act on a body to the motion of that body. All right, so equation of motion has a standard form where we'll put a function of the displacement, the velocity, and the acceleration. All of that on the left-hand side. And then this is equal to some function of time. That would be like external forcing acting on a system, plus any constants, such as gravity. Gravity might be a constant force. So as an example, we could have a harmonic oscillator with the equation of motion mx double dot plus bx dot plus kx is equal to p times the sine of omega t. So that's our harmonic external forcing minus mg, and that is our constant due to gravity. All right, we're going to move on and take a look at work and energy, and then this will lead us into Lagrange's equation. Start off with kinetic energy. This is the energy of motion. So it's the energy that is associated with the motion of a body. We defined our kinetic energy to be T is equal to 1/2 m times the velocity vector r dot dotted with itself plus 1/2 I of the center of mass times the angular velocity vector dotted with itself. And since we really only dealt with 2D, this becomes, or planar motion specifically, 1/2 m times r dot dotted with itself plus 1/2 IC times omega squared, where omega squared is the angular velocity of the body. If you're dealing with a rigid body that's pinned at a particular location, you can use this formula. This formula will bake into it the parallax theorem. You could alternatively ignore the first term and focus only on the second term, but switching this IC to IO, or whatever point you're rotating about, and you then apply parallax theorem to that moment of inertia. All right, we also looked at potential energy. This is the work that is done by conservative forces in a system. And generally, this is related to energy being stored in the system. We looked at energy from 3 different conservative forces. The first was gravity, which we'll just say V sub g is equal to mgh. In this case, we needed to choose a reference configuration, so a position for the system where the gravitational potential energy was 0, and then we considered how that potential energy changes from that position. And then also, if we're dealing with rigid bodies, for compound rigid bodies, actually, is what I meant to say. For compound rigid bodies, you can either compute the compound center of mass and then apply gravity there, or you can do it by components and then add those all together. So you can either use the center of mass for the whole system or components. And they're both equivalent. For springs, our potential energy, which I'll call V sub s, this is in general going to be 1/2 k times the deformation of the spring squared, or we can say x2 minus x1, that quantity squared. That's for a translational spring, or for a torsional spring. We'll get a very similar thing, except that we're going to have thetas instead. So we'll get Vs is equal to 1/2 kt times theta 2 minus theta 1, that quantity squared. For a polynomial spring, nonlinear polynomial spring, we would end up with quantity Vs is equal to alpha divided by beta plus 1 times x to beta plus 1, where again here beta is some positive, beta is a positive integer. I mentioned you can generalize this for beta being any value. You can also generalize, well, I said that when we dealt with the force, you can do the same thing with the energy as well. You can also generalize so beta doesn't have to be an integer. All right, we also dealt with the energy that's dissipated by non-conservative forces, or specifically dissipative forces such as damping. These are things that will remove energy from the system. So viscous damping or friction are two examples of these types of forces. In this case, we can write that our dissipated energy, dE, and sometimes we'll write 1 to 2, and sometimes we'll just leave that out. In this case, the dissipated energy is going to be the integral from time t1 to time t2 of the velocity, r dot, at the location of the force, the velocity of that location dotted with the force, dt. That is what it is in general. For a viscous damper, or if F is equal to B x dot, let's say, then our dissipated energy will be equal to B times the integral T1 to T2 of x dot squared dt. Which is an integral that nobody has solved. So there is a solution, but nobody knows what it is. We haven't figured out, as a species, we haven't figured out how to solve this integral. But you can do other techniques to show that it does exist. So we would just leave it as an integral, and in practice, you'd compute it numerically. All right, let's take a look at the work done by external forces. These are generally going to add energy to the system, though you could tune your external force in a way that it could remove energy as well. But in general, they're going to add energy. So we'll just say generally add energy to the system. The reason why I say that is because if you want to use an external force to remove energy, you've got to tune that force to precisely line up with the response to the system, precisely oppose that response. Whereas any generic input is just going to add energy. All right, so in this case, we'll just write that the work, or W, is going to be equal to the integral from T1 to T2 of r dot dotted with the force, dt. That r dot is the velocity where the force is applied. If it's a particle, it's just the velocity of the particle. If it's a rigid body, well, then it depends on where that force is applied. So we'll specify where r dot is the velocity vector at the location of the force F. And so for our external force that I wrote way up above, when we were looking at the equation of motion, the work done by that external force would be equal to the integral. W will be equal to the integral from T1 to T2 of x dot times P times the sine of omega t dt. And again, this is something we would generally compute numerically in practice. All right, for conservation of energy, we are going to have T sub 2 plus a V sub 2 plus the dissipated energy from 1 to 2. This will be equal to the work done from 1 to 2 plus T1 plus V1. So T2, V2 are the potential or the kinetic and potential energies at time T equals T2. T1, V1 are at time T equals T1. This is our full conservation of energy. The summation of the kinetic and the potential energy is also known as the mechanical energy. So this is our mechanical energy at T equals T2. And then on the right, we have the mechanical energy at T equals T1. And then our mechanical energy is conserved if and only if there are no non-conservative forces acting on the system, where non-conservative here includes both external and dissipative forces as well. The system is also called Hamiltonian in that case. And in that case, we'll find that one, energy would be conserved from one time to another, and then the mechanical energy itself is conserved. So T2 plus V2 is equal to T1 plus V1. So I misspoke there. Energy is always conserved, provided you incorporate all of the, in this case, the source, which is our work done by the external force, loss terms from the dissipation, and then the mechanical energy as well. That is always true. Mechanical energy is conserved if there's no non-conservative forces acting on the system. All right, and this puts us into a position to now go through Lagrange's equation, which is an energy-based method for finding equations of motion. It is part of a field called analytical mechanics, which really uses energy-based techniques to find equations of motion. We first described and discussed what are known as generalized coordinates, which we'll use Q sub I here in order to define our kinetic and potential energies for the system. So we wrote that our kinetic energy T will be some function of the generalized velocities Q1 dot up to Q sub n dot. And our potential energy is some function of the generalized displacements Q1 and Q2, comma up to this Q little n. From here, we're going to define our Lagrangian, which we'll use L, and L is equal to the difference between the kinetic energy and the potential energy, or T minus V. And then Lagrange's equation is d over dt times the quantity partial L over partial Q sub I dot minus partial L over partial Qi is equal to a capital Q sub I, and this is for I equals 1 to up to n. All right, so when we compute Lagrange's equation or apply it, we are going to treat Q sub I and Q sub I dot as independent in computing these derivatives. And then this capital Q sub I is the generalized force, which we found using principle of virtual work, which we'll go over in a moment. We have a general solution procedure for applying Lagrange's equation. We're going to first again define a coordinate system. From there, we're going to determine position vectors. And third, we're going to compute our velocity vectors. We won't need acceleration vectors in this case. And again, these first three steps belong to kinematics. After we compute the velocity vectors, we'll then go and compute the kinetic energy, the potential energy, and the virtual work done by non-conservative forces. It's the virtual work done by non-conservative forces. From here, we can go and compute our Lagrangian. All right, compute the Lagrangian. And then 6, we're going to apply Lagrange's equation. So the benefit of using Lagrange's equation over Newton's second law is that you'll end up with the equations of motion in the simplest form, and without having to worry about any kind of constraints acting between them. It automatically will give us the simplest form of the equations. So there really is no simplification needed here. The output of the Lagrange equation is the simplified equations of motions. And we could call this kinetics, but also analytical mechanics. All right, we're going to take a look at what principle of virtual work said. So when we wrote principle of virtual work, we had some delta Wi. The delta implies that it's a virtual work. This is equal to F sub I dotted with delta Ri, where R, the vector Ri, is the position vector for the force that's being applied. Relative to center of mass, typically. And we're going to do this over every single force. So we listed here with the subscript I, so I will equal 1 to however many forces are applied to the system. All right, so this delta character acts like a differential, but it produces virtual displacements. So specifically, if this vector R is a function of our generalized coordinates, or just let's say a generalized coordinate Q, then delta R, which is a function of Q, is going to be equal to the derivative of R with respect to that coordinate Q multiplied by a delta Q. So for example, if R is equal to the cosine of theta, then delta r will be equal to this delta applied to the cosine of theta, which will then be equal to the derivative of cosine with respect to theta, which will be minus sine theta, then multiplied by a delta theta. And that's where our virtual displacement parameter comes from. So if our position vector or position vectors are vectors of multiple coordinates, let's say q sub k, from k equals 1 to lowercase n, and then there are going to be capital N position vectors, then we will find that the virtual work, delta W, and this is the total virtual work, not just an individual one, is then going to be the summation across the coordinates, so from k equals 1 to little n, applied to the summation across the forces of I, so I equals 1 to capital N, of the quantity, the force F sub I, dotted with the partial of R sub I with respect to the partial Q sub K, that multiplied by delta QK, and then everything within this little blue brace, that is Q sub K, which is the generalized force for the coordinate Q sub K, little q sub K. So I'll give you a little example here. So if we have a force, F of t, let's say is equal to P times the sine of omega t in the I hat direction. And then our position vector R depends on two coordinates, let's say theta 1 and theta 2. And those are our two generalized coordinates. Theta 1, theta 2. And let's say this is equal to the function sine of theta 1 minus theta 2 plus the cosine of theta 2. All of that in the I hat direction plus cosine theta 1j. And this is just an arbitrary force, an arbitrary vector that I made up to illustrate the point. In this case, our virtual work, if we apply that formula, is going to be, we get delta W equal to our force F dotted with the partial of R over partial theta 1. That multiplied by delta theta 1 plus F dotted with partial R over partial theta 2. That multiplied by delta theta 2. All right, so partial R over partial theta 1. This will be equal to cosine theta 1 minus theta 2. In our I hat direction minus sine theta 1 in the j hat direction. And partial R over partial theta 2. This will be equal to minus cosine theta 1 minus theta 2 minus sine theta 2 times I hat, and then plus 0 in the j hat direction. So then our virtual work, delta W is going to be equal to P times the sine of omega t times the cosine of theta 1 minus theta 2 times delta theta 1 plus the quantity minus P sine omega t times the quantity cosine of theta 1 minus theta 2 plus sine theta 2, where I've pulled that minus sign out, put it in front of the P. All of that multiplied by delta theta 2. And so everything inside this first square bracket, this is going to be our generalized force for theta 1. So it will show up on the right-hand side of Lagrange's equation for theta 1. And then everything in the second set of square brackets, that is our Q theta 2. And it is the generalized force acting on theta 2, and will show up on the right-hand side of the second Lagrange equation, the one that is for theta 2, for this system, whatever it is. All right, any questions here? Okay. In that case, we can move on and take a look at chapter 2, which is where we focused on single degree freedom vibrations. We considered just harmonic oscillators like the one shown here, with damping, with a grounding stiffness, some external forcing acting on it. In this case, the equation of motion is mx double dot plus vx dot plus kx is equal to, in this case, f times the cosine of omega t. And then we also need to prescribe some type of initial conditions. And we'll just say here that x of 0 is equal to x sub 0, and then x dot of 0 is equal to v sub 0. You could technically also, instead of prescribing, let's say, initial velocity, you could prescribe some displacement some other time as well. But you're generally not going to see stuff like that. You generally just see initial conditions. In general, our equation of motion may have a complicated set of parameters. And so the general form of our equation of motion will have a bunch of stuff multiplied by x dot, a bunch of stuff multiplied by x dot, and then a bunch of stuff multiplied by just x, equal to some force f of t, we'll say. And so then everything in front of this x dot is considered to be our mass. Everything in front of the x dot term is considered to be the damping coefficient, or B or C, depending on what you want to use. And then everything in front of x would be considered the stiffness for the system. So the stiffness doesn't just have to be K, it could be some complicated expression. This is what happened on the first midterm, where the parameters for that system had a whole bunch of stuff. All right, so the oscillator is going to have two things, always. First, it's going to have a natural frequency. Which we will say is omega sub n. This is equal to the square root of the stiffness divided by the mass. So that means everything in front of x divided by everything in front of x double dot. And generally the units for this, well, the units are radians per second, unless we prescribe that it's non-dimensional. The second thing the oscillator will have is a damping ratio. Which we use zeta to represent. So zeta is going to be equal to our damping coefficient B divided by 2m times omega n. And then this is also equal to B divided by 2 times the square root of Km. These are equivalent expressions. All right, so we're going to look at free response, and then we'll go on and look at forced response. For free response, everything was really determined by zeta, or the damping ratio. We had three different cases. The first was when zeta was less than, or was greater than 0, but less than 1. This is our underdamped case. The second case is when zeta is equal to 1. That's known as critically damped. And then the last case is when zeta is greater than 1. This is what we call overdamped. And I didn't include here when zeta is equal to 0, which is the undamped case. So the underdamped case is the only one that leads to periodic oscillations or vibrations. And in the other two cases, these lead to aperiodic motion. Without any oscillations. This will be a little bit more specific here. Because you can encounter systems that are oscillating aperiodically. Not in anything we covered in this class, but in general they exist. All right, so look at case 1 here, which is our underdamped case. In this case, our oscillator is also going to have a damped natural frequency, which is related to the natural frequency and the damping ratio. And we'll call this omega sub d. This is equal to omega n times the square root of 1 minus zeta squared. And in this case, the displacement of our oscillator is going to be x of t equal to e to the minus zeta omega nt. times the quantity x0 times the cosine of omega dt plus the fraction v0 plus zeta omega n x0 divided by omega d times the sine of omega d times t. All right, moving on to critically damped, which is when zeta was equal to 1. There is no damped natural frequency anymore because there's no more oscillations in the system. So we'll just give what the displacement is. In this case, our x of t is equal to the quantity x0 plus the quantity v0 plus omega n times x0. All that multiplied by t. And then everything inside the square brackets multiplied by e to the minus omega n t. Again, this is the case where zeta is equal to 1. So for critically damped, this is the response that will take the least amount of time to go from some non-zero amplitude down to a 0 amplitude, which we'll see on the next page when we look at the phase space, as well as when we look at the time response. Third case, overdamped. This is for zeta greater than 1. In this case, the displacement of the oscillator is going to be x of t is equal to some c1 times e to the minus zeta plus square root zeta squared minus 1. All that multiplied by omega n t plus some c2 times e to the minus zeta minus the square root of zeta squared minus 1. All that multiplied by omega nt. And I believe that in this first term, there should not be a minus in front of zeta. It should just be zeta plus that square root. And then here, the C1 is equal to a big fraction with x0 omega n times the quantity zeta plus the square root of zeta squared minus 1 plus v0. Then all that divided by 2 omega n times the square root of zeta squared minus 1. And then C2 is going to be equal to a big fraction. Hold on, I don't think there's a minus up here either. Actually, I need to check that. All right, there may or may not be a minus sign up here and up here. I need to go back and check, and I'll update you on Monday on that. It should be correct in your notes from chapter 2, so it's just not, there's a minus sign in one of mine and not in the other one, and that shouldn't be the case. Or maybe it is correct and it's just confusing me. All right, anyway, for C2, we're gonna get minus x0 times omega n times zeta minus the square root of zeta squared minus 1 plus v0 divided by 2 omega n times the square root of zeta squared minus 1. And then beneath that, I just plotted what these different responses look like in solid black right here. That is our undamped response. In this case, the amplitude of the response is never going to decay to 0. It's just going to continue forever. With an underdamped response, we will have some oscillation, and that amplitude is going to decay in time. Also, due to that damping, the frequency is a little bit smaller than omega, so it stretches out. Critically damped, shown over here. This response decays to 0 the fastest, and then overdamped has the same type of shape as critically damped, but it takes longer to reach 0. You can also see this in the phase portrait or the phase plane shown on the right here, where you can see that for an undamped, you get this circle because it just stays the same forever in terms of amplitude. For underdamped, we'll get this spiral in towards 0. We're plotting velocity versus displacement. Critically damped will take the shortest amount of time to reach that 0, and then you can see overdamped overshoots that. All right. Take a look at forced response, and then we'll go to base excitation, and then we'll probably stop at that point. All right, so forced response, we're going to have a free response component plus a steady state response. We'll write that x of t is going to be equal to some big X sub 0 times e to the minus zeta omega nt times the cosine of omega sub d minus omega sub dt minus phi sub 0 here. In this case, we are already assuming that the system is underdamped. So we've already built that assumption into this. So let's just write that, assuming zeta is less than 1, which is pretty much always the case. Like I mentioned, for most systems, the damping ratio is less than 0.1%. So zeta is like less than 0.01. So that's our free response term plus our steady state, capital X times the cosine of omega t minus some phase phi, where omega here is our forcing frequency. This here is our free response. And then the second term is the steady state response. All right, so when we deal with forced response, we are generally just going to be only concerned with the steady state. We're not so much going to care about the free response because the free response dies out in time, whereas the steady state does not die out over time. And that's why we call it steady state. So I'm going to write down what the values are for the steady state amplitude and the steady state phase, and then I already wrote them out for you for the free response because they're much longer and we also don't really care about them. All right, so x here for our steady state amplitude is going to be a fraction with the forcing amplitude f in the numerator divided by the quantity k minus m omega squared, that little quantity squared, plus b squared omega squared. All of that divided by, or raised to the 1/2 power, so we're taking a square root in that denominator. This is the magnitude, well, if we divide by f, we will get here the magnitude of our frequency response function for this oscillator. And then we can also express this in terms of the natural frequency and damping ratio. In that case, we have to scale the force by m. You could also multiply it by k and find a similar expression here. And in this case, in the denominator, we're going to get the quantity omega n squared minus omega squared, this quantity squared, plus 2 zeta omega n omega, that quantity squared. And then all of that raised to the 1/2 power, or there's a square root down there as well. We use this to look at resonance, where if zeta was equal to 0, when we found that when omega was equal to omega n, suddenly the response amplitude blew up to infinity because we were dividing by 0. When we had damping and zeta was not 0, the response didn't blow up to infinity, but it still was very, very large, and as a result, system would still break, is what we said. All right, the phase is going to be defined as the inverse tangent of the quantity c omega k minus m omega squared. And that's equal to the inverse tangent of 2 zeta omega n times omega divided by omega n squared minus omega squared. All right, and beneath this I have included the plots for the steady state amplitude, which we went through when we did chapter 2 for varying zeta values here. This is plotted on a linear frequency scale, which is what we did in chapter 2. When we did Bode diagram, we looked at a log scale for frequency. And to the right, I plotted the phase variable as well. And you can see here that when we cross the natural frequency, the phase is at pi over 2 in this case. All right, we're gonna go through base excitation and then we'll be done for the day. And I'll also add that all of these equations are in your notes from chapter 2 and whatever chapter we're on, so none of this is new. So if you missed something, you can just go refer to that and pull it from there. I mean, I literally copy-pasted from the notes. So, all right, so the equation of motion for base excitation is going to be mx double dot plus cx dot plus kx. That's just our general harmonic oscillator. But then this is equal to c times y dot, which is generally some function of time, plus k times y of t. And in this case, we're treating this as an external force. And so y of t is here some input. A common example for base excitation is a quarter car model where you have a tire or a wheel that's rolling over some road, and the road is varying in height. And then you have some input through the wheel that then transfers from the suspension into the vehicle. That's an example of like a base motion. Okay, so we looked at the case where y of t was equal to some capital Y times the sine of omega t. So we just looked at a purely harmonic input in this case. In this case, we then looked at the steady state displacement, which right is xss, x sub ss of t is equal to big X times the sine of omega t minus phi. And then our goal is to find expressions for capital X and for phi, which is what we did, although we looked at the ratio capital X over capital Y, which we called the displacement transmissibility. This is equal to the equation, or the fraction, k squared plus c omega squared in the numerator, divided by k minus m omega squared, that quantity squared, plus c omega quantity squared, all of that raised to the 1/2. With what we've done since chapter 2, you would now be able to relate this to a transfer function of the system and also a frequency response function. I mean, that's exactly what this is, although this is the magnitude of that transfer function or frequency response function. This is then equal to, if we write it out using natural frequency, we're going to get here omega n squared plus the quantity 2 zeta omega n omega, that quantity squared, divided by omega n squared minus omega squared quantity squared plus the quantity 2 zeta omega n, omega quantity squared, all that raised to the 1/2. And then the phase phi here is going to be equal to the inverse tangent of the fraction m times c omega cubed in this case, and then divided by k times k minus m omega squared plus and that should be squared plus, actually that should not be squared, plus c omega, this quantity squared. Actually, I'll check to make sure that k minus m omega squared, that quantity isn't also squared. All right, we got one more thing to write out, and then we'll be done. Or one more thing to talk about as well. We got the inverse tangent of the quantity 2 zeta omega cubed divided by omega n cubed plus quantity 4 zeta squared minus 1 times omega n times omega. And then I've included the plot of what the displacement transmissibility looks like and then what that phase looks like for this system. And you could go and produce Bode diagrams as well for this.